Yeah, thanks. It's really a great pleasure to visit Berkeley in this very nice time because in Waterloo last week still snowing. And so it's really a very stimulating workshop. And so today I'm going to discuss some work with my student here and on this universal wave function overlap and its application to the two-dimensional and mainly three-dimensional topological order. So I think now it's kind of well known that the symmetry breaking state does not describe all phase. So there are phases like in quantum Hall states, in some kind of organic triangular lattice, or in the Herbert-Smith side, there may be some quantum phase which is beyond symmetry breaking description. This kind of new kind of quantum state matter is called have new kind of order as topological order.
Question.
Yeah.
You never mentioned Fermi liquids. I mean, wasn't
Fermi
that?
liquid is gapless, and I should mention superconductor.
Yeah.
Superconductor is the first discovered topological ordered states. And it's very irony that the symmetry breaking theory is developed to describe a superconductor, which is topologically ordered. And not quantum Hall, so I should really add a superconductor in this list. So what is the picture for topological order? So here we try to give some kind of microscopic picture for topological order. So maybe let's write down one thing. Here's some example, but let's consider another example, which is consider a wave function, which is constant. When you have a manifold wave function which is constant, that really means boson condensation. So that means all the boson occupy momentum equals 0 states. So that's boson condensed states. The boson condensed states actually is a product states. It starts on every site. We have a superposition for 0 boson, 1 boson, 2 boson, and the product state of this superposition of bosonic states give us this wave function, which is a constant amplitude. And so one way to make this one is a short-range entangled. So one way to make this long-range entangled or something topological order is a very general way, is to scramble the phase. So actually, you already heard that this morning. We will do the quantum Hall state like maybe 2. We will change the wave function from 1 to something with this kind of phase oscillation. It's like we scramble the phase. When you scramble the phase, you may get some kind of long-range entanglement. That's very generally. And there's another way to do it. It's like we described here. One is that certainly when you have a fixed spin configuration like this, like spin all pointing up, that's a product state. It's not a long-range entanglement, not topological order. So one way to make them to have long-range entanglement, have topological order, to add entanglement, basically we make superpositions. And we can do that to the extreme. We consider all possible superpositions of all possible spin up and down. But then if you do that, you do too much, because such superposition turns out to be the spin in x direction is unentangled. So therefore, to make a long-range entanglement, we need to sum over a subset. We don't sum over everything. We should not overdo it. And we can sum over a subset, and then to get some kind of long-range entangled states. And so this is another construction. In contrast to this scrambled phase. Here we scramble the phase wave function, and here we pick a subset to do superposition. So one very natural choice would be we only sum over a spin configuration which form loops. So like the spin down is a background, and the spin up form loops. And we only sum over all these loop configurations. So that's one way to make a so-called string liquid. And the string liquid can be this so-called topological ordered or these very funny states. Or more generally, we can allow string to branch, and sum over this string length. And we can get even more general topological ordered states. So this kind of general picture. But certainly when you do that, you don't, maybe sometimes you get something interesting, sometimes you get something boring, you know. So we need something more quantitative to describe this kind of string liquid superposition. So, so how to do that? Well, it's like you know, the string liquid is like a collective dancing, you know, quantum fluctuation. It's not like walls, just like superconducting walls. So there's two bodies dance around each other. But here is everybody dance around each other. But when you describe a dancing pattern, usually we don't describe the motion of everybody in a dancing party. We just describe the dancing rules. So everybody follows the same dancing rules, then you describe the dancing pattern. And so here I try to use this local dancing rule to describe this wave function for string liquid. So that's one idea. So certainly first rule is that all the spin form loops. So that's it just form loop, no end. So that's the first rule. The second rule is that otherwise they dance pretty much freely, in the sense that the string have different shapes. So the amplitude is not penalized. So they all have same amplitude, even when they have same shape, different shape. And also the string can reconnect. Even when string reconnect, these two configurations have a same amplitude. So this like a local rules which is specify the global wave function. So actually, if you implement these two rules, immediately you see that the global wave function is a superposition of loops with equal amplitude. Because when you make this kind of change, you change the number of loops. Say if you change from here to here, you get one more loops. So when you add a loop or subtract loop, they have same amplitude. Then and this first rule says that when the loop changing shapes, they have same amplitude. So basically, everything has same amplitude. So this is a simple dancing rule describe one particular wave function. And but you can change the dancing rule. When you change the dancing rule, then you get another wave function. So one change is that to add the minus sign when the string reconnect. So when string reconnect, we say the wave function change sign, amplitude changing sign. And then this way you get this kind of wave function where the amplitude wave function is always the same, it's 1, the absolute value. But however, the changing sign. For all number of loops, the wave function amplitude is minus sign. For even number of loops, it's plus sign. The reason for that is that whenever you do this reconnection move, the number of loops changes by 1. And then you say the wave function changing sign. So every time you increase or decrease the loop, you get this the sign change. And so therefore we have these two local dancing rules and describe two global wave functions. And then the issue is that if these two wave functions have belong to the same phase or different phase, what their property and etc. So that's one thing. And here I also want to point out that the first dancing rule actually also applies to a higher dimension. So in 3 dimensions, this rule works. But the second rule doesn't. Because it's like here. Because if you do this, I think when you do the reconnection move, the number of loops do not change in 3D. And if wave function changing sign, then there's an inconsistency. So this is kind of interesting. Although these two rules are very simple. And the second rule only consistent in 2 dimensions, but not in 3 dimensions. Okay. So actually there is something, there are consequences. There's a reason behind this. Is that this wave function contains samyans. We know samyang only exists in 2 dimensions. They don't exist in 3 dimensions. And the first wave function only contains fermions, which can exist in 3 dimensions. So first wave function exists in any dimension. Okay. But anyway, so here but these 2 examples really pose an issue. Is that when we know the wave function exactly, we're still facing an issue how to extract physical information like a quasi-particle statistics, fractional charge, or some kind of measurable topological property from the wave function. How to describe the topological order in this wave function. So there's issue here. Yeah. So any question here? Okay. So so how to characterize some kind of topological invariance which distinguish wave function basically? Here I just give a definition of topological invariance. So topological invariance in general is some kind of property of ground states, such that this property is invariant under any local perturbation of Hamiltonian. So that's kind of topological invariance. Okay. So can we find such a topological invariance? And basically, this topological invariance would kind of define the topological order. So at the beginning, one topological invariance was this ground state degeneracy. If you put the system on the torus engineered Riemann surface in 2 dimensions, you find that there's a nearly degenerate ground states. And degeneracy became more and more exact when the sequence size became bigger and bigger. And the amazing thing about the degeneracy is that this degeneracy do not change under any perturbation. At any local Hamiltonian local perturbation, you cannot split degeneracy. So I have this amazing, robust ground state degeneracy. But once you have this degenerate ground state, you can squeeze more out of it. And you can also have this kind of non-abelian geometrical phase. This non-abelian geometrical phase is really the following. Because once you have a degenerate ground state, that's naturally give you some kind of subspace in the Hilbert space. That's representing degenerate ground states. Okay, you have subspace. And then you start to deform, like when I have a torus, you start to deform a torus by changing the boundary condition. And then this degenerate subspace would kind of embed differently in a total Hilbert space. You can rotate. Okay. And then when you deform torus to this shape, then you find that this kind of torus is the same as an old torus if you just relabel sides a little bit. So basically you get a non-trivial loops. From here to here, you get non-trivial loops. Then this subspace have these spaces. These spaces start to rotate, then back to the same subspace, go back loop. And this you can define non-abelian geometrical phase, which is described by a unitary matrix. So it turns out that this unitary matrix is also robust against any perturbation up to the phase. So total E1 phase is not robust because when you do the rotate, the energy of the system may change. And the integration of energy gave you this U1 phase. And the different paths gave you different integration energy, so the phase is totally undetermined. But the relative phase do not depend on the path and do not depend on the local interaction. Yeah?
So your perturbations will not split the degeneracy?
Yeah, this is assumption.
It's an assumption.
Yeah, so such thing exists. So the first thing exists. Basically is that there are such states, there are such Hamiltonian which have this spectrum.
Okay.
And the amazing thing is that any perturbation delta H cannot split degeneracy.
So you can
The Hamiltonian with such property exists.
But you can write down such a Hamiltonian?
Yeah, we can write down. So such Hamiltonian exists. So this is kind of surprising. But once you agree that such Hamiltonian exists, with such that degenerate ground state do not depend on any local perturbation, then it's easier to understand why the relative phase is robust. Because any perturbation cannot split degeneracy. So all the degenerate ground state, when they rotate around, they acquire same abelian phase. So their relative phase is fixed.
So you can write a local Hamiltonian, prove that it's gapped,
Yes.
and also prove that it has a degenerate ground state that is robust under perturbation.
Against any perturbation, yes.
So this has been
But
in the same.
my proof is this. It's not at the level for mathematical physics proof. It's a physicist wishful thinking.
Can one write down? I mean, one could write down the Hamiltonian, presumably, right? I mean,
Yeah. Like a Torah code is one such example.
Not that one
you
can,
like.
like it has been written down.
Torah code.
Yes, the Torah
Or
code
quantum
example.
Hall wave function, like with a, at the beginning, really for quantum Hall wave function with a Coulomb interaction, we believe 2D electron gas with Coulomb interaction would have this property, and that's what quantum Hall state is about. Yeah. And so because of the robustness of degeneracy, so even relative phase of this matrix is robust. So certainly one can also do this 90-degree rotation. You can do similar thing. So actually, up to the phase, this S and T matrix, S is for 90-degree rotation, T is for this shear deformation. They actually generate so-called projection rotation of a modular group. Yeah. And so therefore, this contains much more information, and there's a belief this may contain all the information. So in 2 dimension, the projection rotation of a modular group probably classified all 2-dimensional topology order. And this basically gave us kind of mathematical definition or the macroscopic definition what is a topology order. Basically, it's projection rotation of a modular group. Okay. So actually, recently, people have proposed many different ways to compute this non-abelian geometrical phase, and in the Berkeley group, they have this minimum entanglement states plus this 90-degree rotation or 60-degree rotation. You can compute that, and one can also use volume polarization or some DMRG, also related DMRG calculation. So there's several ways, because at the beginning, compute this non-invariant phase is very difficult, and people don't know what to do. But recently, this numerical method, especially DMRG method, became very powerful. So one can really do some good computation. And here, what I'm going to discuss is yet another way to compute this non-abelian geometric phase. And in this way, we think this is pretty simple. And so what we do is just wave function overlap. Okay. And so the starting point is that suppose I consider a state on a torus. Okay. And we have degenerate ground states. The degenerate ground states are really is its psi alpha. So the alpha labeled the different degeneracy. Okay. Then how to compute this projection representation for modular groups? How do you compute this SNT matrix basically? Well, it's very simple. You just do this, compute this matrix element. That's all. So what is the matrix element? So what is the T operator? The T operator basically is the following. We kind of, I don't know how to say. We kind of relabel these sites. Then compute overlap wave function using relabeled sites. So usually when you calculate normal wave function, this side and this, so this side hit this side. When you consider the overlap, these two sides. So this side fit this side aim to this side. But however, when you do this T operation, you say this side corresponds to this side. And so basically okay, let me say that you compute so T times a wave function is equal to another wave function, which is so this is a new wave function, okay, where this z prime is really correspond to so I have two components, x prime, y prime. So x prime can be x plus y. So y prime is a y. Some kind of shear deformation. And And when you calculate overlap wave function, you calculate this overlap. It's this function with variable z, but with a star. Then another wave function with indirectly it's function of z, but it's dependent on z through z prime. But this wave function is function of z, and this wave function is function of z prime. They are the same wave function. And so this overlap with alpha beta basically is what I'm describing here.
So if I look at the detailed color here, it doesn't look like they're just a rotation or a shear. Like the red bonds.
Yeah. So this is okay. So this picture have a meaning. Okay. Let me tell the meaning of this picture. Is that so here in this picture we try to describe how the loop liquid changes. And so here we have this triangular lattice. And this red bond are just two different loops. Then under shear deformation, you can find this loop became this loop. So that's okay. But this loop break up. So as a result, is that only this loop, because on this lattice you also have loop liquid. So this loop and this loop have overlap. But this loop have no amplitude here because they break up. So therefore, this overlap is very tiny. So there's a local difference. And this also demonstrates that we cannot do it with on the square lattice. On the square lattice, every loop break up, so overlap equal to 0. So we have to consider some lattice, so there's some overlap. On the square lattice, this happens to be 0, so it doesn't work. So we have to do this.
So you don't share the lattice kind of with the lines, you just share the lattice sides, but the underlying lattice you don't share.
Yeah. So we really share the lattice, but however we share the lattice, we're still thinking this as the same triangle lattice.
Exactly, because if you would share the lattice...
Because if you really share everything, this bond should become this bond, and we say this bond do not exist.
Exactly.
And so that's why some loop don't change, probably. And but on this lattice, there's some subset loop on these two lattices overlap. So this overlap is non-zero, basically. So same thing here again. So so this loop can be changed to this loop, but this loop again became just a breakup. But anyway, these two overlap non-zero. So there's a volume term. Yes.
What's the meaning of the lines that you have, say the black lines? Are they? Do we have to think about this is the toric code and
Yeah.
they are plaquette and star template?
Exactly. So this is really toric code, but on the triangular lattice.
Okay, so what specifically, say the S matrix, it would be a 90-degree
90-degree rotation,
But
yes.
how is it that the
But this black line just an aid of I. Basically, we say my toric code is not all the loops. Only loops follow these black lines. Only this kind of red
How does a
line.
90-degree rotation
Yeah.
mess up any loop?
that's
No, 90-degree rotation because if you do 90-degree rotation, this link would become this link,
yes.
and this link is not there actually. And this will be the forbidden loop in the original lattice. But this loop is okay. This loop is compatible with 90-degree rotation symmetry.
But the
So
question is,
this loop, so there's some subset loop which is survive rotation, so have overlap. Some other loop don't have overlap.
but this 90-degree rotation, is it a permutation of sides to sides?
Yes, it is permutation side. The reason, the problem is that when we do this, if you really do this rotation, we actually have a loop of this shape, have this kind of loop.
Yes.
But this kind of loop do not exist in the original lattice. So this kind of loop have no overlap. I mean the loop which involving this kind of bond.
That's fine.
Because the original lattice don't have this kind of loop and this kind of loop. After 90 rotation, you'll start to have this kind of loop, And this loop is not there. So this kind of weight is lost. So when you do overlap, they don't have weight.
So this explains that the overlap is going to be exponentially suppressed.
Exactly.
But the question still is do you just perform a 90-degree rotation?
That's right. Because the Hamiltonian is not 90-degree rotation invariant because we don't have bond in that direction.
But what happens on square lattice? Why is it 0?
A square lattice, this is good. S is good, but T is not good. Because when you on square lattice, the loop has the vertical bound. When you do shear deformation, you should have loop with a 45-degree bound. But on a square lattice, we just don't have that kind of loop. And so
So that would mean that the overlap is really zero.
Zero,
on
yeah.
any side.
for any size, yeah, it's really 0. But this is an accident because the Tor code is too perfect. So in generic states, you should have some non-zero overlap.
So if you have the toric code with a small perturbation in the Hamiltonian,
Yeah,
still
it should be okay.
lattice, it should work.
Yeah, that should work. Yes, but the Tor code is ideal thing, and so sometimes a generically non-zero overlap may happen to be 0. So that's why we have to do this a little more complicated thing. And then, so the basic proposal is very much like a topological entanglement entropy. When you do the overlap, this overlap is exponentially small, so something like e to the minus total area of the system. Then the sublink term is like a linear in L. Then there's a constant term, and a 1 over L term, and etc. And here the claim is that we don't have linear term. I don't know why, we just don't have it. And the constant term is here. So this S and T are really constant term. And there's a 1 over L term and etc. Okay. And then the claim is that this area term certainly is not universal. So these two coefficients are not universal. But the constant term, this S and T, this constant term is universal. And it's given by this ST matrix, and that's it. So this is a kind of claim. So therefore, you just need to compute this, as in quantum information language, the fidelity of wave function. Then you just get it. And yeah. So here we just we do some here just in a very simple example. So, and I'm glad Norbert discussed this yesterday. So we have this loop gas, and but here we just put some weight here. If G equal to 1, that means you have equal weight superposition of loops. If G is 0, that means we have no loops. So as the changing value of G, you may get the phase transition from the phase with loop liquid to the phase with no loop. But then how do you get different degenerate ground state? The different degenerate ground turn out to be dependent on the winding number of loop all the way around torus. So like a Wx is how many times the loop wind in x direction, and Wy is how many times loop wind in the y direction. Then you can modify the wave function depending on its winding number with some plus sign, minus sign, etc. So this way you can get the 4 orthogonal wave function. And they locally look the same. So locally they look the same, so they're degenerate. But globally they are orthogonal, so that's how you get the 4-4 degeneracy here. And then, so once you get these 4-4 degenerate ground states, you can compute this overlap. And then as a function of G, and to see what happens. So actually this is what one see. So when G is very small, so actually S and T just all equal to 1. And this is again we heard this yesterday, because when G is small, you only have small loops. So actually the weight for the loop wind around the whole torus almost 0. So adding this minus sign don't do anything. So actually this 4 state actually is almost in the same direction. So they are the really same states in one phase. So that's why the overlap all equal to 1. They are really same states. But however, when G is large enough, then this kind of sign change will make them orthogonal. And that's where this phase transition happens. And then after phase transition, then you obtain a different S&T matrix. Okay. So this is not in the canonical quasi-particle basis, or not in the basis of minimal entangled state. But however, this is the canonical basis in the tensor network. In tensor network also choose certain canonical basis, and this is the canonical basis for tensor network. And so one can see this phase transition very clearly. But this is the first wave function where the reconnection don't change in sign. So one may wonder if the reconnection of string changing signs, you get different wave function. Maybe this ST matrix should be different. So indeed, it's different. So for the second wave function, this is what we get. So almost the same thing, except in this loop liquid phase, only here this is +1, here is a -1, this is a +1, this is a -1. It's just these changes. Okay, so indeed that calculating all wave function overlap can really distinguish different topological phase. So this may be a very effective way to diagnose the many-body wave functions. And so here there's one thing. We have to generate all the degenerate ground state to do this. If you only have one variation of wave function, we cannot do it. So there's a challenge, is that to use this method, we have to generate degenerate ground state. How to do that? Well, you can always do exact angulization. Certainly, when system big enough, you get degenerate ground state. But since it's never big enough, you don't clearly see the separate ground state. Actually, tensor network is a very, very good method. Actually, tensor network, you can also use tensor network to do this calculation. The good thing about tensor network is that in the tensor network calculation, one somehow don't even see this non-universal factor. It's automatically renormalized away. You almost theoretically compute this volume independent part. And the reason for that is that when you consider tensor network wave function, we don't care about the scale of a tensor. We can also always multiply every tensor by some kind of scaling factor. Okay. But when you do that, you multiply the overlap wave function by a factor proportional to the volume, exactly proportional to the volume. So therefore, multiplying some kind of scaling factor to each tensor is really like shifting this volume part, which you don't care. We usually just normalize tensor into some standard normalization. We just get rid of that part. So therefore, using tensor network, if you don't care about the normalization of tensor, you directly obtain this SNT universal part. And I'm really glad Norbert described this very carefully yesterday, is that when you have a tensor network, certainly if you only have one tensor, you connect them, you just get one state. So how do you get other states? Then there's one thing, is that if a tensor network describes a topological order, then this tensor have a special symmetry property, which we call the gauge symmetry property, or this is G-injectivity property. And so basically it says that somehow if we multiply some kind of unitary transformation on these 4 legs, in this particular way, the whole tensor don't change. The old tensor, the new tensor, and this kind of 4 unit transformation, they're invariant. And this is very mysterious, why it has to be that. And so I think we don't know full story here yet. And but just this is very important. To describe any topological order, you need this. One related thing is that it really became the disconnection between the tensor and the Hamiltonian. Because topological order is the robust property of Hamiltonian. We change Hamiltonian, then some physical don't change. But tensor describe a wave function. We cannot say the topological property is a robust property against any change of a tensor. Because the change of a tensor and change of Hamiltonian are not equivalent. And we know that certain change in the tensor, in particular, if a tensor have this symmetry property, and if a change in tensor which break this symmetry property, this kind of change can never be realized by a change of Hamiltonian. So because this kind of a subtleties, and so we require that. But on the other hand, we really don't know I think this probably still not fully resolved. I mean, the full story, I mean, exactly what kind of change of tensor correspond to the perturbation of Hamiltonian and which is not in the reason is following. When you're using this kind of tensor to describe this wave function, and this symmetry actually became a so-called gauge group. So therefore, the many-body wave function described this kind of tensor network can be a gauge theory, and the gauge group is happen to be this symmetry. Okay. And so we know there are some other topological order states like Fibonacci string net states. We don't know what is gauge group for that. So for that one, I don't know what is symmetry condition in the tensor network distribution of Fibonacci states, for example. And but we don't know there's a Fibonacci state have a tensor network description, but what kind of gauge or what kind of gauge structure protect that is very tricky. I think Frank probably have something.
Well, you two will talk about this tomorrow, actually.
Yeah, there's the more general string waves.
Exactly,
I understand
exactly.
that's the more that's
this
probably
has
the
been
better
resolved. Indeed,
rather than
this
the
has been
symmetry.
resolved.
Yeah, that's a really good story. Yeah, and but on the other hand, it's also puzzling. I say, well, you consider tensor with the symmetry, then you only describe topological order states. So you put in topological into a wave function by hand. So what you're detecting? But actually, that's not the case. Even when the tensor have a symmetry, here I want to emphasize that this kind of transformation is not irreducible. They are reducible representation. They include the block which is trivial representation. There are some blocks which don't do anything. Okay, so you can imagine if this tensor have all the weights in the block where the u and v act trivially, so these two transformations don't do anything. So therefore, even though we require tensor to have this symmetry, the low energy field theory don't have to be gauge theory. They can be confined fixed. Okay. So therefore, this method allows us to study the confinement, deconfinement transition of a particular gauge group. So there are some limitations here. I try to describe a limitation of tensor network approach. That's if you consider tensor with certain gauge symmetry, then you cannot study all topological order. You can study topological order describe this kind of gauge group. Or its confined phase means no topological order. Or some subgroup. Sometimes some subgroup of this G maybe a surviving topological order. So actually, this is not too bad. If you choose a very, very big symmetry group, which contains all kinds of a subgroup, then this symmetry group would allow you to study all this gauge group, which is subgroup of this big symmetry. So you can still study the phase transition among different gauge symmetries. So this basically is a kind of program. Yes.
Is it clear it has to be a subgroup? Couldn't it be just a sub-algebraic structure which is contained in that group action?
Yeah, I don't know. It's right now I'm still thinking as a gauge symmetry, so as a group, and I don't want the string picture would give something more general. Yeah, and that's a. The point is that this is easy to do because this is like a symmetry. So when you're writing code, it's easier to implement the tensor which is satisfied by the symmetry property. When you have some more general structure, it's a challenge.
No, my question was just that it could be that a group symmetry as a subsymmetry contains things which are actually not group-like and give you other ones.
Yeah, that I don't know. Yeah.
I mean, you can get string nets, for instance, by putting group symmetry, Semyon models, for
Yeah.
instance, by putting group symmetries and using the right subsymmetry.
Yeah, actually, double Samyang. Yeah, I'm glad you mentioned it. In double Samyang model, this group has to be Z4. you know, there's something one can one will study that. Yeah. Okay. So,
Over there.
but yeah.
Do you need the wave function in terms of groups explicitly, or
No,
let's say I had Hagime ladders.
you don't have to. So this is the key. So actually, so with this understanding, your purpose is start with tensor with certain internal symmetries. But this tensor could describe trivial states as product states. But tensor with internal symmetry have a potential to describe a gauge theory of that symmetry. So if you suspect your state have like a Z3 gauge symmetry, then you better start with tensor with a Z3 internal symmetry. And then try to anticipate whether maybe Z3 would pop up. If you choose the wrong internal symmetry, you'll probably never get the right topology order. So this is the choice. But certainly, if you really don't know what kind of topology you have to pick a very big symmetry group and pay a lot of expense on the very high internal bound dimension. And but in principle, one can do something like that. But certainly, there's an issue about doing this. Can you describe all the topology order like Fibonacci? You know, Fibonacci have a group has a gauge theory description. I think this must SO3 level 2, SU3 level 2 or something like that. And so maybe some SU3 symmetry can capture Fibonacci. This I don't know. And but this really, but the message here is that in order to study topology order, you need to start with tensor with some symmetry. Then play the game. Yeah. Okay. And
So wait, so you're saying you might be able to do final states in the same way?
no.
What you're saying?
Yeah, here I'm hiding. So all these states, I think, have a gapable boundary. So entanglement spectrum should have a gap. The chiral state. So yeah, we couldn't do chiral states here. And so actually that's why to study tensor network representation of chiral states is very important, so that I can bring that into this framework. But seems that's difficult. Yeah. And so that's remain to be something in the future.
Fibonacci is chiral.
Fibonacci not chiral. It's double Fibonacci. Yeah. So
Double.
yeah. So when I say Fibonacci, I mean it's a double one. And so how do we generate the
Sorry, well, I mean, SU3 level 2 is chiral, of course.
yeah, then the double that. So that's I think when I say Fibonacci, I mean this SU3 level 2 double that, then double. And so once we have this tensor with symmetry, then we can just we can put that tensor on the torus, and then say adding this kind of symmetry transformation, but only along a line. So basically, we modify the tensor from T to T prime because this tensor with this U attached is different tensor. So we have a tensor network which is not translation invariant. But then you see this is very strange because you are describing translation invariant system and you suddenly modify the tensor along this line. That seems very strange. But actually, even along this line, the wave function is the same as this part. The reason is that this line can be moved away because this tensor have this symmetry property, so you can include this pair of V star, U star, such that because when a tensor is surrounded by the full transformation, they are the same tensor as a T. So only the tensor near the boundary is different. So you can see you can move this line around. So actually, the wave function, local wave function here, is the same as here, which is same as any other place. So this line is invisible. So this is a way to create orthogonal states, but locally indistinguishable. So when you have tensor network with the symmetry, you can do that. So this also, again, is explained very well by Gilbert yesterday. So this way, so equipped with this way of generate degenerate states, then you can compute overlap, you can get everything. Yes.
So what if the internal symmetry is confined, as you explained? So we say that adding this line does not create another orthogonal state?
Okay. That's a tricky thing. You get another state which may not be orthogonal in some limit. If adding this line makes it orthogonal, that means in topological phase. And then there's overlap gives you ST matrix. But in the confined phase, adding this line don't do anything. You may change wave function a little bit, but they're mainly in the same direction. So therefore, you don't get orthogonal states, so then ST matrix becomes degenerate. Yeah. So after getting this ST matrix, we say what we can learn from this ST matrix. Unfortunately, I don't have too much time. And so actually we can do this in any dimension. So in 2 dimension, the T is like this shear deformation, S is like 90 degree rotation. But in the 3 dimension, on the 3D torus, we have similar modular transformation, or more generally it's called a mapping class group, which again generated by 2 elements. One is a shear deformation in the XY plane, just like the 2D case. Then another is this cyclic exchange of XYZ. This is a cyclic exchange of XYZ. So these 2 generate a 3-dimensional mapping class group, which is SL3Z. In 2D is SL2Z. Just these 2 groups. So there's a conjecture that for the topological order with a gapable boundary, again, we don't have a chiral state here. Then the representation of this SL2Z, not necessarily, the representation of a mapping class group may classify topological order completely. It's just a conjecture. But mapping class group can be for any topology. Don't have to be 3D torus. But in 2 dimension, looks like just 2 torus already enough. In 3 dimension, I don't know whether 3 torus is enough, or maybe I consider more arbitrary, more general topology. But in general, we believe that the representation mapping class group, this collection of representation mapping class group should classify all the topological order with gapable boundary. And okay. Maybe let's skip this. So what we can learn from this ST matrix? One is that from ST matrix we can learn that this say how many quasi-particles do we have? Okay. So actually the ground state degeneracy on the torus gave us a number of type of quasi-particle. And one, I don't have a good way to understand this, but the party line is that you can drill 2 holes on the sphere. On the sphere, there's no degeneracy. You will drill 2 holes on the sphere and attach a handle. Then that's make whole thing be like a torus. And then you can also view this structure as there's a quasi-particle quasi-hole kind of goes through this. This handle can create a pair of quasi-particle quasi-hole. And a different way to create a quasi-hole corresponds to degeneracy on the torus. So in this way, the number of quasi-particle type and degeneracy on the torus are somehow related. So this is kind of party line understanding. Maybe there's a better way.
The better way is to use the Berliner algebra.
Well, it's here.
That's a formula. That's the Berliner formula. The algebra is algebra operations which act on the different states and map them into each other.
Like this modular transformation.
No. You create a quasi-particle anti-quasi-particle pair on the torus. You drag it around,
okay.
Reannihilate, and then you change the state on the torus.
So that's involving braiding then?
Well, then if you do the same operation, so you can take some trivial state, create a quasi-particle, anti-quasi-particle pair,
yes.
You drag it around adiabatically, and you annihilate them again.
Yes.
Now, if you consider this on different cycles, then these operations don't commute because of the braiding.
Okay, okay.
So this gives you an algebra which acts on the states on the torus. It's called the Berliner algebra.
Okay, yeah.
And it's using that Berliner derived the Berliner formula.
Okay,
So
yeah.
this establishes all of these things.
So that's correspond.
This was understood in 1989.
Okay, so that's involving this this 2 pi braiding of one particle around
It
another.
does involve that, yes.
Yeah. Okay, so that's basically encoded in this S matrix. I think that is how how this fusion rule is obtained from this S matrix. But anyway, so so the eigenvalue of a T matrix is a spin of this topological excitation, and then this fusion, when you fuse two quasi-particles, you can get another quasi-particle. Then this fusion algebra, this fusion coefficient, can be obtained from this S and T matrix. Okay, so so basically, this is really trying to say that if you know the S and T matrix, you can obtain a lot of this topological information of quasi-particle excitation. So so here we try to do a similar thing for the 3 dimension. So maybe that's another message. So in a 3 dimension, we have this 3-dimensional S and T matrix. But here S is different. S corresponds to the permutation of X, Y, Z. T is a similar, just a Dehn twist or shear deformation in the X, Y, Z plane. So, so the question that if you know the 3-dimensional S and T matrix, what you can say? What you can say about topological excitation? Okay, so so as there's many ways to look at it. So the one way we find it very useful is to consider so-called dimension reduction. So basic idea is that we consider 3D torus as a 2-dimensional torus with one direction very small. If one direction is a very small loop, the whole thing like a 2-dimensional system. So then we try to view this 3-dimensional system as a 2D system. Then we say, what kind of 2D system do we get? So that is a basic idea. Okay. And then to do that, it's very convenient to consider this SL2Z subgroup of SL3Z. And because SL2Z subgroup is generated by this 90-degree rotation in XY plane. And again, the same shear deformation in XY plane. So these two operations generate a subgroup of SL3Z. Okay. So we will generate a subgroup. Then you can consider, because this S and T matrix form representation for SL3Z. So you can consider the branching rule of this representation, irreducible representation for SL3Z into the some kind of direct sum of irreducible representation of SL2Z. Okay. Then we have this picture is that this representation SL3Z describes a 3D topological order, and the SL2Z describes this 2D topological order. So this branching rule for representation suggests this branching rule of the topological order. So you are using C to describe a different topological order, 3D or 2D. Sometimes you say what that means. Okay. So what it should really mean is the following. So let's consider, suppose we don't have 2 terms here. Suppose we have C1 and C2 have 2 terms. So what do you mean by C3D equal to C1 2D plus C2 2D? What do you mean by that? You know, this C1 2D plus C2 2D. What is the meaning of this? So you can consider you have a Hamiltonian, depend on one parameter. When you're changing the parameter, you find in one region, this C1 2D is a ground state. Then when you're changing parameter, then you have a first order phase transition. Then the C2 became ground state. Then right at the transition point, then these 2 states have the same energy. You have accidental degeneracy. Okay. So the spectrum at the transition point is like a continuum, and you have a degenerate ground state, but this belongs to C1 2D. But there's accidental degeneracy, which belongs to C2 2D. They just accidentally degenerate. So this whole thing is a C1 2D plus C2 2D. So this is the physical meaning of this notation. So basically what I really try to say is that we can view the three-dimensional topology order as a 2D topology order with accidental degeneracy. And this accidental degeneracy is lifted when this when this direction became very small. When the direction very small, you could have operator which wrap all around this small direction. That would be local operator. They will lift the degeneracy. But however, if this third direction is very long, no operator wrap around it. So this accidental degeneracy is protected. So that became degeneracy of a three-dimensional topology order. So therefore, this kind of symmetry, this reduction from SL3Z to SL2Z, tell you how the 3D topology order reduced to 2D topology order. Then, for example, as an example, that we can have a 3D topology order which is a S3 gauge theory. Okay, and so we just denote this topology order as this C S3. Okay, and then we say that then we find that the degeneracy on the torus is 21. So this R3D is 21 by 21 matrix. When you reduce into the SL2Z, it became this 8 by 8, 4 by 4, 9 by 9 block. Became 3 block. Okay, and these 3 block happen to be the ST matrix for the 2D gauge theory. The gauge group happen to be the S3 gauge group in 2 dimensions, or Z2 gauge group, or Z3 gauge group. Okay, so therefore this dimension reduction for S3 of a 3 dimension give you this give you this 2-dimensional gauge theory, but with different gauge group. Okay, actually this is very easy to understand because when you do dimension reduction along every loops, because this is a discrete gauge theory, so along the loop, the Wilson loop is trivial. But however, along the non-trivial loops, like in x, y, z direction, the Wilson loop may be non-trivial, so like this gx, gy, gz. Okay. And if in the small loop, this flux through this small loop is identity, then the symmetry not broken. The identity is commute with everything. So you have no symmetry breaking, so you get a 2-dimensional S3 gauge theory. But however, this flux here can be non-zero, can be some kind of order 2 element. So this is I think this is order 2 element. It can be one of order 2 element. But if there's a flux in this order 2 element of S3, then it's like you break the gauge symmetry. But you break down to Z2 because this order 2 element commute with self. So S3 is break down to Z2 gauge theory. So therefore you get this Z2 topology order. Similarly, you can have the flux in this another conjugacy class is order 3 element. And then you break S3 down to Z3, so you get this one. So it's just a very easy way to understand that. Yes?
So if you did a simpler example, let's say you did a Z2 gauge theory.
Yeah.
So you get 2 sectors, you get 2 copies.
Yeah, you get 2 copies of the same thing. It's just 2-dimensional Z2. Yeah. Yeah.
So, if the group has a center, then the center will be included in either.
Yeah, I think that symmetry is unbroken for all the sectors.
So then that means these sectors are sort of not independent, but
no, they are independent. Sometimes these 2 groups could be the same. It happens. So that means you have accidental degeneracy of 2 toric code, for example, just accidental degeneracy. Okay. So maybe just a last point is that so let's skip that, and maybe let's do this. Okay. So actually this 3D to 2D reduction encode this braiding and fusion of strings. Okay. The reason is found. So let's consider the situation where the small circle is identity, is a trivial. Okay. then we can think where, in this case, the 2D theory is a quantum double of S3. So there's 8 kind of particle, trivial one plus 7 non-trivial one. Okay, this is some label. But we know that from dimension reduction, all these 2D particle must come from 3 dimension. So there's a 3 dimension have a charge. 3 dimension is S3 gauge theory, have a charge. So the charge will naturally become charge of 2D. So that actually is these 2A are charges. But the 3 gauge theory also have the string. This gauge theory have vortex lines. And but this vortex can wrap around these small loops, and it looks like a point particle in 2D. So actually, some point particle like this B and C actually come from a 3D vortex line. So this B and C 3D actually 3D vortex line, just like that. And some other particle actually is a fusion of a particle and a vortex line. So that's these 2 particles is like a fusion line. So once you understand this correspondence, then things become very simple. Is that the fusion of braiding of a 2D particle, which we know, we know much better for 2D topological order, is that then it became a fusion braiding of a 3D particle and the loops. In particular, in 2D, we know that the fusion of C and the C give us in 2D give us 1, A1, and C. So that means in 3 dimension, we have a loop. These 2 loops fused together. We have a 3 degeneracy, 3 degenerate case. Could be trivial, could be charge, and could be C itself. So therefore, this 2-dimensional fusion, we can read the 3-dimensional fusion from the 2-dimensional fusion. So that's one thing we can learn. And as the last point, because in 3D, we can also shrink particle, shrink loop into a point, then fuse 2 points. So actually, from this fusion between loop and particle, we can guess that the shrinking, for example, the shrinking of a 3D loop, this C loop, should be equal to 1 and degenerate with another charge. So this loop, from far away, looks like accidental degeneracy of a trivial particle and the charged particle. Okay. And if you think this kind of shrinking rules, this shrinking rule will be compatible with the fusion. We don't know how to derive this directly, but we just make a guess, and this guess consistent with this kind of fusion. Okay. So therefore, that's maybe the main message. That so from the dimension reduction, we can learn something about the fusion and the braiding of loops. And just for the reference, maybe, so if this loop have non-trivial flux, that's correct a fusion braiding string with another string threading through it. So in the last transparency, I assume there's no flux in this small circle. Then that means you have a string with no threading. But when you have a flux through this circle, the 2D series are different. So you have different fusion and braiding. So that means when the 2 loops are threaded with another loop's strings, their fusion and braiding is modified. So this is recently, in the Michael Levin's paper and in Rin's paper, they have this 3-string fusion and braiding, mainly braiding basically. And so this is again, this feature is encoded in the dimension reduction. Okay, I think over time I should stop here. Yeah.
We have time for a question or two while Schelling comes up. You're next, right?
The fusion of 2C gives you several components. So that's a sign that this C is now being as a 2D particle. Then we believe they are braiding as a 3D string also now being, because the fusion space multi-dimension, the non-abelian barrier space should be the same as 2D. Yeah. So they're really non-abelian braiding.
Just a comment. So Thorsten Wald, who's sitting somewhere here, would present a poster in which he shows that for these Gaussian chiral PEPs,
yeah,
you also have some strings that you can move and with the same properties basically, and defining the generate states, etc., etc.
Oh, I see.
About that.
I see. So the way you can use that to generate degenerate ground state, even for casual text.
Yes.
And
Right, and then you can put strings around the torus that
Okay.
you can move around because the translational environment is
Yeah,
basically
yeah.
the same properties.
Okay.
But these are strings, these are not product operators, like in the case of the Tori code.
Yeah.
So that's
Oh, there's
string.
yeah, I have the string operator. I see.
Okay, let's thank Shalom again.
Yeah. Thank you.